Today I am discussing about the most important chapter of science class 10th, from which minimum 2 to 4 questions are asked in every exam. So it is most important for every exam. So let's start without wasting of time. So let's start. Chapter number is 11. Chapter name is electricity. Electricity has an important place in modern society. जो इलेक्ट्रिसिटी विद्युत का जो है बहुत ही बड़ा महत्वपूर्ण रोल है, स्थान है इन मॉडर्न सोसाइटी। ये जो मॉडर्न सोसाइटी है इसमें इलेक्ट्रिसिटी का बहुत ही महत्वपूर्ण योगदान है। गॉट इट? इट इज अ कंट्रोलेबल एंड कन्वीनियंट फॉर्म ऑफ एनर्जी फॉर अ वैरायटी ऑफ यूजेज इन होम्स, स्कूल, हॉस्पिटल्स, इंडस्ट्रीज एंड सो ऑन. It is controllable and convenient form of energy for a variety of uses. इसकी बहुत सारे यूजेज होते हैं इन होम्स, घर में, स्कूल में, हॉस्पिटल्स, इंडस्ट्रीज एंड सो ऑन. गॉट इट? नेक्स्ट, व्हाट कॉन्स्टिट्यूट्स इलेक्ट्रिसिटी? व्हाट? हाउ डज इट फ्लो इन एन इलेक्ट्रिक सर्किट? व्हाट आर द फैक्टर्स दैट कंट्रोल or regulate the current through an electric current circuit? Got it? Electric circuit. In this chapter we shall attempt to answer such questions. We shall also discuss the heating effect of electric current and its application. Okay, इस चैप्टर में हम डिस्कस करेंगे हीटिंग इफेक्ट के बारे में ऑफ इलेक्ट्रिक करंट, विद्युत धारा के, और इसके एप्लीकेशन क्या होते हैं इसी के बारे में बात करेंगे. नो वी विल डिस्कस अबाउट इलेक्ट्रिक करंट एंड सर्किट. ओके, वी आर फैमिलियर विद एयर करंट एंड वाटर करंट. वी नो दैट फ्लोइंग वाटर कॉन्स्टिट्यूट्स वाटर करंट इन रिवर्स. सिमिलरली, इफ द इलेक्ट्रिक चार्ज फ्लो थ्रू अ कंडक्टर, फॉर एग्जाम्पल through a metallic wire, we say that there is an electric current in the conductor. In a torch, we know that the cells or a battery, when placed in proper order, provide flow of charge or an electric current through the torch bulb to glow. We have also seen that the torch gives light only when its switch is on. What does a switch do? What? A switch makes a conducting link between the cell and the bulb. A continuous and closed path of an electric current is called an electric circuit. Okay? Now, if the circuit is broken anywhere or the switch of the torch is turned off, the current stops flowing and the bulb does not glow. जब किसी सर्किट कहीं से ब्लॉक हो जाता है, मतलब टूट जाता है एनीवेयर, और द स्विच ऑफ द टॉर्च इज टर्न्ड ऑफ, यदि हम टॉर्च के स्विच को ऑफ कर देते हैं, द करंट स्टॉप्स फ्लोइंग, करंट जो फ्लो करना होता है, बहना जो होता है, बंद हो जाता है, एंड द बल्ब डज नॉट ग्लो, और बल्ब जो है नहीं चमकता है. हाउ डू वी एक्सप्रेस इलेक्ट्रिक करंट? हम इलेक्ट्रिक करंट, विद्युत धारा को कैसे एक्सप्रेस करेंगे उसके बारे में बताएंगे. इलेक्ट्रिक करंट इज एक्सप्रेस्ड बाय द अमाउंट ऑफ चार्ज फ्लोइंग थ्रू अ पर्टिकुलर एरिया इन यूनिट टाइम. इन अदर वर्ड्स, इट इज द रेट ऑफ फ्लो ऑफ इलेक्ट्रिक चार्ज in circuit using metallic wires. Electrons constitute the flow of charge. However, electrons were not known at the time when the phenomenon of electricity was first observed. So, okay. Next, electric current was considered to be the flow of positive charge, and the direction of flow of positive charge was taken to be the direction of electric current. Conveniently, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons which are negative charge. Got it? Next, if a net charge q flow across any cross section of a conductor in time t, then the current I through the cross section is I equal to q by t या q equal to it. The SI unit of electric charge is coulomb. SI unit क्या होता है इलेक्ट्रिक चार्ज का? coulomb, which is equivalent to the charge contained in nearly 6 into 10 to the power 18 electrons. We know that an electron possesses a negative charge of 1.6 into 10 to the power 19 coulomb. The electric current is expressed by a unit called ampere, A, named after the French scientist André Mary. Ampere 1775 to 1836, 1 ampere is constituted by the flow of 1 coulomb of charge per second. That is 1 ampere equal to 1 coulomb per 1 second. Small quantities of current are expressed in milliampere. 1 mA equal to 10 to the power minus 3 A, or in macroampere. 1 macroampere equal to 10 to the power minus 6 A. An instrument called ammeter measures electric current in a circuit. एक इंस्ट्रूमेंट होता है उसका क्या नाम कहते हैं? एमीमीटर. एमीमीटर AMMETER एमीमीटर मेजर इलेक्ट्रिक करंट. वो उस क्या काम है? इलेक्ट्रिक करंट को मेजर करना, मापना इन अ सर्किट, किसी भी सर्किट में. इट इज ऑलवेज कनेक्टेड इन सीरीज इन अ सर्किट थ्रू विच द करंट इज टू बी measured. Okay. Next, show the schematic diagram of a typical electric circuit comprising a cell, an electric bulb, an ammeter, and a plug key. Note that the electric current flow in the circuit from the positive terminal of the cell to the negative terminal of the cell through the bulb and ammeter. Okay. Next, figure here 11.1, a schematic diagram of an electric circuit comprising cell, electric bulb, ammeter, and plug key. Got it? Next, example 11.1, a current of 0.5 ampere is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flow through the circuit. Solution is, we are given I equal to 0.5 angstrom, T equal to 10 minute, equal to 600 second. From equation 11.1, we have Q equal to IT. Here, Q equal to IT. Got it? So, I equal to here 0.5 A into 600 S. Then it is equivalent to 300 coulomb. Got it? Next, now we will discuss about electric potential and potential differences. What makes the electric charge to flow? What? Let us consider the analogy of flow of water. Charges do not flow in a copper wire by themselves, just as water in a perfectly horizontal tube does not flow. If one end of the tube is connected to a tank of water kept at a higher level, such that there is a pressure difference between the two ends of the tube, water flow out of the other end of the tube. Okay. Next, for flow of charge in a conducting metallic wire, the gravity of course has no role to play. The electron move only if there is a difference of electric pressure called the potential difference along the conductor. Okay, next. This difference of potentially may be produced by a battery consisting of one or more electric cell. The chemical action within a cell generates the potential difference across the terminal of the cell, even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charge in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to expend its chemical energy stored in it. Okay. Next, we define the electric potential difference between 2 points in an electric circuit carrying some current as the work done to move a unit charge from one point to the other. Okay. Next, potential difference V between 2 points equal to work done W by charge Q. V equal to W by Q. Okay. The SI unit of electric potential difference is volt. इलेक्ट्रिक पोटेंशियल डिफरेंस की SI यूनिट क्या होती है? वोल्ट, जिसे V से डिनोट करते हैं, कैपिटल V. नेम्ड आफ्टर एल्सेंड्रो वोल्टा, 1745 to 1827, an Italian physicist. 1 volt is the potential difference between 2 points in a current carrying conductor when a joule of work is done to move a charge of 1 coulomb from one point to the other. Okay. Next, therefore 1 volt equal to 1 joule by 1 coulomb. So it is 1 volt equal to 1 joule per coulomb. Got it? Next, the potential difference is measured by means of an instrument called voltmeter. Okay. The voltmeter is always connected in parallel across the point between which the potential difference is to be measured. Okay. Now we will discuss about circuit diagram. Okay. We know that an electric circuit as shown in figure 11.1 here comprises a cell or a battery, a plug key, electrical components as and connecting wires. It is often convenient to draw a schematic diagram in which different components of the circuit are represented by the symbol conveniently used. Okay. Conventional symbol used to represent some of the most commonly used electrical component are given table 11.1. Symbol of some commonly used component in circuit diagram. Component here symbol. An electric cell, इसका symbol क्या होता है? एक साइड प्लस एक माइनस. ये प्लस वाला साइड का जो ये चिन्ह रहता है बड़ा रहता है और इधर माइनस वाले का छोटा रहता है. गॉट इट? नेक्स्ट, अ बैटरी और अ कम्बिनेशन ऑफ सेल, इसका किस तरह से रहता है? बड़ा छोटा बड़ा छोटा. गॉट इट? बड़ा साइड में प्लस चार्ज और जो छोटा साइड है उसके माइनस चार्ज. नेक्स्ट, प्लग की और स्विच ओपन, इसका कैसा रहता है? सिंबल ये. गॉट इट? नेक्स्ट, प्लग की और स्विच क्लोज्ड, इसका सिंबल क्या है? ये. अ वायर ज्वाइंट, इसका सिंबल क्या है? ये. वायर क्रॉसिंग विदाउट ज्वाइंटिंग, इसका सिंबल क्या है? ये. गॉट इट? नेक्स्ट, इलेक्ट्रिक बल्ब, इसका सिंबल ये रहा. ओके. नेक्स्ट, अ रेसिस्टर ऑफ रेसिस्टेंस आर, इसका सिंबल ये. गॉट इट? वेरिएबल रेसिस्टेंस और रिहोस्टेट, इसका सिंबल ये या ये. ओके. एमीमीटर का सिंबल ये, उसको गोल कर दिया गया दोनों साइड से लकीर खींच दिया गया, एक साइड प्लस एक साइड माइनस। गॉट इट। वोल्ट मीटर में V को गोल कर दिया गया, इसके एक साइड मतलब लेफ्ट साइड प्लस और राइट साइड माइनस चार्ज कर दिया गया। गॉट इट। नो वी विल डिस्कस अबाउट ओम लॉ, ओम्स का नियम। Is there a relationship between the potential difference across a conductor and the current through it? What? Let us explore with an activity. Activity 11.1. Set up a circuit as shown in figure 11.2 consisting of a nichrome wire XY of length say 0.5 meter and a meter, a voltmeter and 4 cells of 1.5 volt. Each nichrome is an alloy of nickel, chrome, manganese and iron metals. First use only one cell as the source in the circuit. Note the reading in the ammeter I for the current and reading of the voltmeter V for the potential difference across the nichrome wire XY in the circuit. Tabulate them in the table given. Okay. Next connect to cells in the circuit and note the respective reading of the ammeter and voltmeter for the values of current through the nichrome wire and potential difference across the nichrome wire. Got it? Next, repeat the above step using 3 cells and then 4 cells in the circuit separately. Calculate the ratio of V to I for each pair of potential difference V and current I. Okay. Next, number of cells used in the circuit ampere. Next, current through the nichrome wire I wire V volt. Next, potential difference across the nichrome. Next, V by I volt by ampere. Okay. Plot a graph between V and I and observe the nature of the graph. Got it? Next, in this activity you will find that approximately the same value for V by I is obtained in each case. Thus, the VI graph is a straight line that passes through the origin of the graph as shown in figure 11.3. Thus, V by I is a constant ratio. In 1827, a German physicist George Simon Ohm 1787-1854 found out the relationship between the current I flowing in a metallic wire and the potential difference across its terminals. The potential difference V across the end of a given metallic wire in an electric circuit is directly proportional to the circuit current flowing through it, provided its temperature remains the same. This is called Ohm's law. In other words, V directly proportional I. V by I equal to constant equal to R. V बराबर I R. Got it? Next, in equation 11.4, R is a constant for the given metallic wire at a given temperature and is called its resistance. It is the property of a conductor to resist the flow of charge through it. Its SI units is ohm, represented by the Greek letter ohm. According to Ohm's law, R equal to V by I. Okay. If the potential difference across the two ends of a conductor is 1 volt and the current through it is 1 ampere, then the resistance R of the conductor is 1 ohm, that is 1 ohm equal to 1 volt by 1 ampere. Also from equation 11.5 we get I equal to V by R. Okay. Next, it is obvious from equation 11.7 that the current through a resistor is inversely proportional to its resistance. Okay. If the resistance is doubled, the current gets halved. यदि हम यहाँ पे रेसिस्टेंस को डबल करेंगे तो क्या होगा, करंट आधा हो जाएगा. In many practical cases, it is necessary to increase or decrease the current in an electric circuit. A component used to regulate current without changing the voltage source is called variable resistance. In an electric circuit, a device called rheostat is often used to change the resistance in the circuit. We will now study about electrical resistance of a conductor with the help of following activity. Okay. Activity 11.2. Take a nichrome wire, a torch bulb, a 10 watt bulb and an ammeter 0 to 5 ampere range, a plug key and some connecting wire. Set up the circuit by connecting 4 dry cells of 1.5 volt each in series with ammeter, leaving a gap XY in the circuit as shown in figure 11.4. Okay. Next, figure 11.4. Nichrome wire, 10 watt bulb, torch bulb. Got it? Complete the circuit by connecting the nichrome wire in the gap XY. Plug the key. Not done the ammeter reading. Take out the key from the plug. Note: always take out the key from the plug after measuring the current through the circuit. Got it? Next, replace the nichrome wire with the torch bulb in the circuit and find the current through it by measuring the reading of the ammeter. Next, now repeat the above step with the 10 watt bulb in the gap XY. Next, are the ammeter reading different for different components? Connect in the gap XY. What do the above observation indicate? What? You may repeat this activity by keeping any material component in the gap. Observe the ammeter reading in each case. Analyze the observation. Okay. Next, in this activity we observe that the current is different for different component. Why do they differ? Certain component offer an easy path for the flow of electric current, while the other resist the flow. We know that motion of electron in an electric circuit constitutes an electric current. The electrons, however, are not completely free to move within a conductor. They are restrained by the attraction of the atoms among which they move. Thus, motion of electrons through a conductor is retarded by its resistance. Okay. Next, a component of a given size that offer a low resistance is a good conductor. A conductor having some appreciable resistance is called a resistor. Okay. A component of identical size that offer a higher resistance is a poor conductor. An insulator of the same size offer even higher resistance. Okay. Next, factors on which the resistance of a conductor depend. Activity 11.3. Complete an electric circuit consisting of a cell, an ammeter, a nichrome wire of length L, say marked 1, and a plug key as shown in figure 11.5. Got it? Here, figure 11.5, electric circuit to study the factor on which the resistance of conducting wires depend. Now plug the key, note the current in the ammeter. Replace the nichrome wire by another nichrome wire of same thickness but twice the length, that is 2L, marked 2 in the figure 11.5. Next, note the ammeter reading. Now replace the wire by a thicker nichrome wire of the same length L, marked 3. A thicker wire has a larger cross-section area. Again, note down the current through the circuit. Next, instead of taking a nichrome wire, connect a copper wire marked 4 in figure 11.5 in the circuit. Let the wire be of the same length and same area of cross-section as that of the first nichrome wire marked L. Note the value of the current. Notice the difference in the current in all cases. Does the current depend on the length of the conductor? What? Does the current depend on the area of cross section of the wire used? What? Next, it is observed that the ammeter reading decreases to 1/2 when the length of the wire is doubled. Okay, the ammeter reading is measured increased when a thicker wire of the same material and the same length is used in the circuit. A change in ammeter reading is observed when a wire of different material of the same length and the same area of cross section is used. On applying Ohm's law, we observe that the resistance of the conductor depends I on its length, second on its area of cross section, and third on the nature of its material. Precise measurement have shown that resistance of a uniform metallic conductor is directly proportional to its length L and inversely proportional to the area of cross section A, that is R directly proportional L and R inversely proportional 1 by A. Got it? Combining equation 11.8 and 11.9, we got R inversely proportional L by A और R इक्वल टू रो L by A. गॉट इट? इसको ध्यान रखना है, ये एग्जाम पॉइंट ऑफ व्यू से काफ़ी इम्पोर्टेंट है. Where rho is a constant of proportionality and is called electrical resistivity of the material of the conductor. The SI unit of resistivity is ohm m. Got it? It is characteristics property of the material, the metal and alloy. Got it? Next, have very low resistivity in the range of 10 to the power 8 ohm meter to 10 to the power 6 ohm meter. They are good conductor of electricity. Insulator like rubber and glass have resistivity of the order of 10 to the power 12 to 10 to the power 17 ohm meter. Both the resistance and the resistivity of a material vary with temperature. Got it? Next, Table 11.2 reveals that the resistivity of an alloy is generally higher than that of its constituent metals. Alloy do not oxidize, burn readily at high temperature. For this reason, they are commonly used in electrical heating devices like electric iron, toasters, etc. Tungsten is used almost exclusively for filament of electric bulb, whereas copper and aluminum are generally used for electrical transmission lines. Got it? Here 11.2 electrical resistivity of some substances at 20 degree Celsius. Conductors, materials, resistivity. इसको आप एक बार गो थ्रू हो जाना है, ठीक. फिर इसके बाद एलओए है, इसके बाद इंसुलेटर है. गॉट इट. नेक्स्ट, हेयर इज एग्जाम्पल, यू कैन गो थ्रू इट. गॉट इट. हेयर इज अ एग्जाम्पल, सम you can go through it. Got it. This is defined here in easy language, no tough. Got it. You can go through it. Next, resistance of a system of resistors. In preceding section we learned about some simple electrical circuit. We have noticed how the current through a conductor depend upon its resistance and the potential difference across its ends. In various electrical gadgets, we often use resistors in various combinations. We know, therefore, intended to see how Ohm's law can be applied to combination of resistors. There are two methods of joining the resistors together. Figure 11.6 here. Okay. Show an electric circuit in which three resistors having resistance R1, R2 and R3 respectively are joined end to end. Here the resistors are said to be connected in series. यहाँ पे आप देख सकते हो R1, R2, R3 जो है रेसिस्टेंस है, ये इन टू इंड जुड़ा हुआ है. तो इस तरह के जो कनेक्शन होगी इसको हम क्या कहेंगे? सीरीज कहेंगे. गॉट इट. इसको ध्यान में रखना है. नेक्स्ट, फिगर 11.7 शो अ कॉम्बिनेशन ऑफ रेसिस्टर्स इन व्हिच थ्री रेसिस्टर्स आर कनेक्टेड टुगेदर बिटवीन पॉइंट एक्स एंड वाई. हेयर द रेसिस्टर्स आर सेड टू बी कनेक्टेड इन पैरेलल. गॉट इट. Resistors in parallel, resistors in series. What happens to the value of current when a number of resistors are connected in series in a circuit? What would be their equivalent resistance? What? Let us try to understand this with the help of a following activity. Okay, 11.4 activity. Join three resistors of different values in series, connect them with a battery, an ammeter and a plug key as shown in figure 11.6. You may use the resistors of value like 1 ohm, 2 ohm, 3 ohm, etc. and a battery of 6 volt for performing this activity. Plug the key, note the ammeter reading. Got it? Next, change the position of ammeter to anywhere in between the resistors. Note the ammeter reading each time. Do you find any change in the value of current through the ammeter? What? Next, you will observe that the value of the current in the ammeter is the same independent of its position in the electric circuit. It means that in a series combination of resistors, the current is the same in every part of the circuit or the same current through each resistors. Got it? Here activity 11.5. In activity 11.4, insert a voltmeter across the end X and Y of the series combination of three resistors as shown in figure 11.6. Plug the key in the circuit and note the voltmeter reading. It gives the potential difference across the series combination of resistors. Let it be V. Now measure the potential difference across the two terminals of the battery. Compare the two values. Okay. Next, take out the plug key and disconnect the voltmeter. Now insert the voltmeter across the end X and P of the first resistor as shown in figure 11.8. Got it? Here, plug the key and measure the potential difference across the first resistor. Let it be V1. Similarly, measure the potential difference across the other two resistors separately. Let these values be V2 and V3 respectively. Deduce a relationship between V1, V2 and V3. Okay. You will observe that the potential difference V is equal to the sum of potential difference V1, V2 and V3. That is the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistor, that is V equal to V1 plus V2 plus V3. Okay. In the electric circuit shown in figure 11.8, let I be the current through the circuit. The current through each resistor is also I. It is possible to replace the three resistors joined in series by an equivalent single resistor of a resistance capital R, such that the potential difference V across it and the current I through the circuit remains the same, applying the Ohm's law. To the entire circuit, we have V equal to IR. Got it? Here, on applying Ohm's law to three resistors separately, we further have V1 equal to IR1, V2 equal to IR2, V3 equal to IR3. Then from equation 11.11, I got it IR equal to IR1 plus IR2 plus IR3. Then RS equal to R1, R2 plus R3. Got it? We can conclude that when several resistors are joined in series, the resistance of the combination RS equal to the sum of their individual resistance R1, R2, R3 and is thus greater than any individual resistance. Got it? Here is some example. You can go through it. Okay. Next, we will discuss about resistors in parallel. Now, let us consider the arrangement of three resistors joined in parallel with a combination of cells or a battery as shown in figure 11.7. Activity 11.6. Make a parallel combination XY of three resistors having resistance R1, R2 and R3 respectively. Connect it with a battery, a plug key and an ammeter as shown in figure 11.10. Also connect a voltmeter in parallel with the combination of resistors. Plug the key and note the ammeter reading. Let the current be I. Also take the voltmeter reading. It gives the potential difference V across the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistors. See figure 11.11. Got it? Here 11.10 is some example of parallel resistors. Got it? Here take out the plug from the key, remove the ammeter and voltmeter from the circuit, insert the ammeter in series with the resistors R1 as shown in figure 11.11. Note the ammeter reading. Okay. Similarly, measure the current through R2 and R3. Let these be I2 and I3 respectively. What is the relationship between I1, I2 and I3? Okay. Here is defined it. It is observed that the total current I is equal to the sum of the separate current through each branch of the combination. I equal to I1 plus I2 plus I3. Let Rp be the equivalent resistance of the parallel combination of resistors by applying Ohm's law. To the parallel combination of resistors we have I equal to V by Rp. Okay. On applying Ohm's law to each resistor we have I1 equal to V by R1, I2 equal to V by R2 and I3 equal to V by R3. Okay. Next, I by 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. Thus, we may conclude that the reciprocal of the equivalent resistance of a group of resistance joined in parallel is equal to the sum of the reciprocal of the individual resistance. Okay. Here we have seen that in a series circuit the current is constant throughout the electric circuit. Thus it is obviously impracticable to connect an electric bulb and an electric heater in series because they need current of widely different values to operate properly. Okay. Next, another major disadvantage of a series circuit is that when one component fails the circuit is broken and none of the component works. If you have used fairy light to decorate building on festival, on marriage celebration, okay, you might have seen the electrician spending lot of time in trouble locating and replacing the dead bulb. Each has to be tested to find which has fused or gone. On the other hand, a parallel circuit divides the current through the electrical gadgets. The total resistance in a parallel circuit is decreased as per equation 11.18. This is helpful particularly when each gadget has different resistance and requires different current to operate properly. Okay. Now we will discuss about heating effect of electric current. We know that a battery or a cell is a source of electrical energy. The chemical reaction within the cell generates the potential difference between its two terminals that sets the electrons in motion to flow the current through a resistor or a system of resistors connected to the battery. We have also seen in section 11.2 that to maintain the current, the source has to keep expanding its energy. Where does this energy go? Okay, a part of the source energy in maintaining the current may be consumed into useful work like in rotating the blades of an electrical fence. Rest of the source energy may be expended in heat to raise the temperature of gadget. Okay. Next, we often observe this in our everyday life. For example, an electric fan becomes warm if used continuously for longer time, etc. Okay. Next, on the other hand, if the electric circuit is purely resistive, that is a configuration of resistors only connected to a battery, the source of energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater and electric iron. Got it? Next, consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V equal to figure 11.13. Let T be the timing during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time small t. Hence, the power input to the circuit by the source is okay P equal to V Q by T equal to VI. Got it? Next, or the energy supplied to the circuit by the source in time T is PT, P into T. Okay, that is VIT. What happens to this energy expended by the source? What? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time T is H equal to VIT. Okay. Here, applying Ohm's law, equation 11.5, we get H equal to I square capital R small t. Okay, this is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance, directly proportional to resistance for a given current, and third, directly proportional to the time for which the current flow through the resistors. In practical situation, when an electric appliance is connected to a non-voltage source, equation 11.21 is used after calculating the current through it using the relation I equal to V by R. Okay, here 11.13, a steady current in a purely resistivity electric circuit. Okay, here is a example of some, you can go through it. Okay, now we will discuss about practical application of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. In electric circuit, the unavoidable heating can increase the temperature of the component and alter their properties. However, heating effect of electric current has many useful applications. The electric laundry, iron, electric toaster, electric oven, electric kettle and electric heater are some of the familiar device based on Joule heating. यहाँ पे बताया गया है जो इलेक्ट्रिक लॉन्ड्री आयरन होते हैं, इलेक्ट्रिक टोस्टर होते हैं, इलेक्ट्रिक ओवन होते हैं और इलेक्ट्रिक केटल होते हैं एंड इलेक्ट्रिक हीटर होते हैं, ये सभी जो फैमिलियर डिवाइस हैं, ये किस पे बेस्ड है? जूल हीटिंग पे। गॉट इट? इसको ध्यान रखना है। द इलेक्ट्रिक हीटिंग इज आल्सो यूज्ड टू प्रोड्यूस लाइट as in an electric bulb. Here, the filament must retain as much of the heat generated as is possible so that it gets very hot and emits light. It must not melt at such high temperature. A strong metal with high melting point, such as tungsten, melting point 3380 डिग्री सेल्सियस। क्या होता है? टंगस्टन का मेल्टिंग पॉइंट 3380 डिग्री सेल्सियस। गॉट इट? इसको ध्यान रखना है। इज यूज्ड फॉर मेकिंग बल्ब फिलामेंट। इसका उपयोग टंगस्टन का कहाँ पे होता है? बल्ब के फिलामेंट बनाने के लिए। द फिलामेंट शुड बी थर्मली आइसोलेटेड एज मच एज पॉसिबल using insulating support etc. The bulb are usually filled with chemically inactive nitrogen and argon gases. जो बल्ब होते हैं उसमें इनएक्टिव नाइट्रोजन और आर्गन गैसेस फुलफिल कर दिया जाता है टू प्रोलॉन्ग द लाइफ ऑफ फिलामेंट। इसको इसलिए भरा जाता है नाइट्रोजन और आर्गन को क्योंकि इसमें जो फिलामेंट होते हैं इसके लॉन्ग लाइफ के लिए। गॉट इट? मोस्ट ऑफ द पावर कंज्यूम्ड बाय द फिलामेंट appears as heat, but a small part of it is in the form of light radiated. Okay. Next, another common application of Joule heating is the fuse used in electric circuit. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point. For example, aluminium, copper, iron, lead, etc. If a current larger than the specified value flow through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal end. Okay. Next, the fuses used for domestic purposes are rated as 1A, 2A, 3A, 5A, 10A, etc. For an electric iron which consumes 1 kilowatt electric power when operated at 220 volt, a current of 1000 by 220 ampere, that is 4.54 ampere, will flow in circuit. In this case, a 5 ampere fuse must be used. ओके, तो ये फैक्ट जो है इसको याद रखना है। इसको ये 220 वोल्ट और 5 एम्पियर और ये 4.5 एम्पियर, इसको ध्यान रखना है। नेक्स्ट, इलेक्ट्रिक पावर। यू हैव स्टडीड इन योर अर्लियर क्लास that the rate of doing work is power. This is also the rate of consumption of energy. Equation 11.21 gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P equal to VI और P equal to I square R equal to V square by R. The SI unit of electric power is watt. Okay, the SI unit of electric power is watt. WATT, watt, इसको कैपिटल W से डिनोट करते हैं। It is the power consumed by a device that carries 1 ampere of current when operated at a potential difference of 1 volt. Thus 1 watt equal to 1 volt into 1 ampere equal to 1 VA. The unit watt is very small. Therefore, in actual practices, we use a much larger unit called kilowatt. It is equal to 1000 watt. Since electrical energy is the product of power and time, the unit of electric energy is therefore watt hour Wh. 1 watt hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt hour kWh, commonly known as unit. 1 kWh equal to 1000 watt into 3600 second equal to 3.6 into 10 to the power 6 joule. Got it? Next, more to know. Many people think that electrons are consumed in an electric circuit. This is wrong. We pay the electricity board or electric company to provide energy to move electrons through the electric gadgets like electrical bulb, fan, engines. We pay for the energy that we use. Okay, here is example. You can go through it. Okay, here you will what you have learned. Here is discuss about it. A stream of electrons moving through a conductor constitutes an electric current. Conveniently, the direction of current is taken opposition to the direction of flow of electrons. Next, the SI unit of electric current is ampere. To set the electrons in motion in an electric circuit, we use a cell or a battery. A cell generates a potential difference across its terminals. It is measured in volt. Okay. Resistance is a property that resists the flow of electrons in a conductor. It controls the magnitude of the current. The SI unit of resistance is ohm. Okay. Next, Ohm law. The potential difference across the end of a resistor is directly proportional to the current through it, provided its temperature remains the same. Next, the resistance of a conductor depends directly on its length, inversely on its area of cross section, and also on the material of the conductor. Okay. Next, the equivalent resistance of several resistors in series is equal to the sum of their individual resistance. Okay. Next, a set of resistors connected in parallel has an equivalent resistance Rp given by 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus dot dot so on. The electrical energy dissipated in a resistor is given by W equal to V into I into T. Okay. The unit of power is watt. W. 1 watt of power is consumed when 1 ampere of current flow at a potential difference of 1 volt. Okay. Next or last, the commercial unit of electrical energy is kilowatt hour kWh. 1 kWh equal to 36 lakh joule. Okay, equal to 3.6 into 10 to the power 6 joule. Okay, got it? So thank you friends. Here is end of my class. So thank you for watching this video. Hope you will learn something new. So Love you guys. Thank you so much.